Welcome to the second part of the intracellular electrophysiology tutorial. In this part, we will focus on the organization of metadata from these experiments in NWB. Specifically, we will look at the question of how can we describe the complex organization of intracellular experiments. Intracellular electrophysiology experiments typically consist of large collections of recordings with varying parameters. We can see an example from the Allen cell types database at the bottom left, where a long square stimulus with varying amplitude is being applied in sequence to a cell, and then the corresponding responses are being recorded. Similarly, we see an example from the Blue Brain project in the bottom right, where a sequence of different stimuli, each with varying parameters, is being applied across different experimental conditions. One thing that is common across these different experiments is that they're typically organized hierarchically by time. And so in this presentation, we're first going to look at how this sort of metadata is currently being managed in NWB. And we're then going to look at upcoming enhancements in the NWB data standard that we have been developing for this use case, and which will become available soon in NWB. The current approach for describing intracellular experiments is based on a sweep table, which you've already seen in the first part of this tutorial. So just a quick recap. The sweep table is a dynamic table which stores for each recording a sweep number and a reference to a corresponding patch clamp series. The sweep table allows us to group patch clamp series that stem from the same sweep together. That is, we can define groups of simultaneously recorded patch clamp series based on the sweep number. So let's just have a look at a simple example. In PyNWB, the sweep table is populated automatically for us as we add stimuli and acquisitions to the file. Each patch clamp series here has a sweep number associated with it, which allows us to automatically add them to the table. For example, here we have a voltage clamp stimulus series with a sweep number of 0 and a corresponding voltage clamp series, which also has a sweep number of 0, which are added to the file where the NWB file adds stimulus and NWB file add acquisition methods, which then in turn populate the sweep table for us. When we record simultaneously for multiple electrodes, then those recordings will also have the same sweep number. But obviously, intracellular electrode that is being used is different for these new patch clamp series. And then as we acquire more data, recordings from different sweeps are distinguished by their sweep number. Since the sweep table is itself a dynamic table, we can easily add custom metadata to it via custom additional data columns using the add column method that is provided by the dynamic table. Some of the advantages of the sweep table approach are that it's simple and easy to use. It allows recordings to be added sequentially as they're being generated, so that this approach is very easily amenable to how data is being acquired. It also allows for custom metadata about the sweeps, and PyNWB conveniently populates the sweep table for us as we add patch clamp series. Some of the things that we would like to improve is that we would like to allow the modeling of the hierarchy of intracellular electrophysiology experiments. The sweep table currently focuses on simultaneous recordings, aka sweeps, while additional details about experiments are up to the user to model via additional custom metadata columns. We also would like to make the relationship between stimuli and responses more explicit. Currently, relationships between stimuli and responses are defined implicitly through the sweep number and intracellular electrodes. What this means is that if we want to identify corresponding patch clamp series, we need to search the sweep table to find all the patch clamp series that have the same sweep number. And then we need to compare those intracellular electrodes of these patch clamp series to identify which ones are corresponding stimuli and response pairs. And the code example shown here illustrates this, where we iterate over the unique set of sweep numbers. We then query the sweep table with the getSeries function to identify all the patch clamp series that belong to a particular sweep, and then we have to iterate over those patch clamp series to relate them based on their electrode. And then finally, we would like to avoid the replication of metadata to reduce the risk of errors. For example, here the sweep number is being replicated across the patch climb series and the sweep table, but also as we add custom columns to the sweep table, metadata that is constant across different sweeps has to be replicated in the table. And so to address these open challenges, we have been working with the community over the last roughly 9 months with a goal to enhance the management of intracellular experiment metadata. These capabilities will become available in NWB soon, so we wanted to give you here a preview of what is coming soon. The approach we have taken for this is that we developed a proposal and we implemented an extension for managing metadata about the hierarchical organization of intracellular electrophysiology experiments. We developed this extension in collaboration with members of the Blue Brain Project and the Allen Institute for Brain Science, and we also posted it for public review to collect feedback and information from the community. And we also performed a review of the extension during the developer hackathon at the Allen Institute for Brain Science in February of 2020. The goals of this effort include that we wanted to identify and define the main levels of the hierarchy of intracellular experiments. We want to enable metadata to be associated explicitly with different levels of the hierarchy. We want to make relationships between the different levels explicit. We also want to make the relationship between different time series, that is stimulus and response pairs, more explicit. And we want to avoid the replication of data in the NWB file to reduce the risk of errors. And then finally, the approach should be backwards compatible with the current NWB standard, and we also would like it to be extensible to allow further standardization of ICEphys experiment metadata in the future. So first, we will define the levels of the intracellular recording hierarchy, which is driven by the temporal organization of experiments. As we define this terminology for these levels, a goal that we had was to define them explicitly and use descriptive terms to avoid collisions with more ambiguous terms such as sweep or sweep sequence, runs, and traces, which can have varying meaning in different recording systems, for example. So we begin with defining the intracellular recordings, which each consists of the intracellular electrode that is being used to record the signal, which is using the existing intracellular electrode as defined in the current NWB file. It also consists of a stimulus and response. Each is a time series that responds a voltage or current stimulation or recorded response with a particular set of parameters. We then have the concept of simultaneous recordings, also known as sweeps, which consist of one or more intracellular recordings. That is, we have a group of stimuli that are presented and responses recorded simultaneously, possibly using multiple electrodes. We then have the concept of sequential recordings, each consisting of one or more simultaneous recordings. This is typically used to represent a set of stimuli that are applied in sequence, often of the same stimulus type. Next, we have repetitions, each of which consists of more sequential recordings. This typically represents sets of stimuli that are applied in sequence as part of an experiment. And then finally, we have the experimental conditions, each consisting of one or more repetitions. This represents a collection of recordings that were acquired in sequence under the same experimental conditions. To describe these different levels and their associated metadata in the NWB, we then define separate tables for each level with cross-references between these tables to explicitly model the relationships and the nesting between the elements at the different levels of this hierarchy. So let's start at the bottom and first look at the intracellular recordings table. In the table, we need to store information about the electrode, the stimulus, and the response, which are stored as object references in the table. So we have a reference to the intracellular electrode, and then corresponding references to the stimulus and the response time series. Similar to the management of time intervals such as epochs and trials in NWB, we here allow the referencing of subranges of a time series by storing the start index and the count in time along with the reference to the time series itself. This is to allow for greater flexibility in the future, as well as to allow for subselection of time ranges if different recordings should not align directly in the file. A new feature that has been introduced here with the intracellular recordings table is the concept of categories, or you might call it subheadings of table. Each category is described by a separate dynamic table which must be aligned. That is, each of these tables has the same number of rows. So what you can see here, there's 3 categories: electrodes, stimuli, and responses. Each of those is being represented in the file as a separate dynamic table, so we can add custom columns to each of those. And then they are required to be aligned by the number of rows. This approach has a number of advantages. First, it supports dynamic metadata for each type of data. That is for electrodes, stimuli, and responses, since each of them is stored as a separate dynamic table, as well as global metadata across the different intracellular recording. It also allows for definition of custom categories, which means we can create completely new dynamic table categories along with this table to capture additional metadata about intracellular recordings. This organization makes the relationship between stimulus and response pairs explicit in the table, meaning they're related by the row index. If I read a single row out of this table, it contains all the corresponding stimulus and response pairs, so that we no longer have to query based on the sweep number. It also allows referencing of temporal subranges in time, similar to the time intervals, which was also not previously supported by the sweep table. It is also compatible with the current approach of patch clamp series types. The main difference is that sweep timbre is no longer used, but it's still being defined in the patch clamp series. The electrode is redundant in the patch clamp series in the table, but we included it in the table primarily because we want to be able to add custom metadata for electrodes, as well as to make querying the table more convenient. And then the sweep table is no longer needed, as the intracellular recordings table supersedes it. Now let's have a look at the other levels, and here we begin again with the intracellular recordings table, and we just show a very simple example of this here. The simultaneous recordings are then defined by a simultaneous recordings table. Each simultaneous recording consists of a set of intracellular recordings which are described via a dynamic table region. That is, we have a column in the table that stores a reference to our intracellular recordings table as an attribute on that column. And then this recordings column stores a variable length set of integer indices, which are row indices, into the intracellular recordings table to define which intracellular recordings belong to a particular simultaneous recording. And then we can define additional custom metadata about the simultaneous recording via additional columns. Similarly, sequential recordings are defined via the sequential recordings table, where each sequential recording then consists of a set of simultaneous recordings. And in addition, we here also define the sweep type that is used for the sequential recording, and it's defined as a separate column. And then we continue this process as we go across the additional levels that we defined. We have the repetitions table, which references sequential recordings tables. And then finally, we have the experimental conditions table, which references the repetition table. And so with this, we now have the full definition of our metadata hierarchy. And so we will next look at how we can use this in code. Like I mentioned before, we implemented this in an extension which is available online, and the code that I'm showing you here is from an example notebook that is included with that repo, in which I included in the heading. So the first step is that we're creating our NWB file, our device, our intracellular electrode, and our patch glimpse series as usual. And we can optionally add them to the file as usual where the add stimulus and the add acquisition functions, although this is no longer required, as adding these recordings to the file is being handled by the intracellular recordings table. So as we add rows to the intracellular recordings table, we're a custom add intracellular recording functions on the NWB file. The function will also automatically add the stimulus and response series to the NWB file if they're not already added to it. And so for intracellular recording, we need to define the electrode, the stimulus, and then optionally the start index and count index for the stimulus, as well as the response and the corresponding start index and count for it. The start index and counts we can omit, and if they're omitted, they're automatically being set to 0 and the total length of the time series. We can optionally also identify the ID that we want to associate with the intracellular recording. If we do that, then that ID must be unique, and by default they're set sequentially in the table. We then next can define custom metadata if we want to for intracellular recordings. We can do this by adding columns to the global table, such as here a recording tag. We can also add custom metadata to the individual categories. For example, here we define a voltage threshold as an example filter on the electrodes, which are added via the category tag to the electrodes table. And we can also create completely new categories in the table by creating a new dynamic table, which here is called recording lab data, which stores a location. In this case, the location where the data was recorded in Middle Earth. And then we can add that table to our intracellular recordings table via the add category function, where the name of the category is the same as the name of the dynamic table. And so let's have a look at what we have so far. We can convert our intracellular recordings table to a pandas data frame for visualization. So what we've created so far is we have an intracellular recordings table that consists of 3 intracellular recordings with the IDs 10, 11, and 12. They have a custom recording tag. They each have the electrode with a voltage threshold custom column, and then the stimulus and response pairs, and the custom category for our recording lab data. So now that we have the intracellular recordings defined, we can populate our simultaneous recordings table. Again, we can here add custom columns to the table if we choose. We can add a simultaneous recording, again, where a dedicated function on the NWB file method called add ICEphys simultaneous recording, which consists of the recordings, which is a list of integers with the row indices. In the intracellular recordings table, we can define a custom ID, and as you can see, we can then also populate the metadata columns that we created for each recording as we're adding them to the simultaneous recordings table. As I mentioned, the recordings here are defined by row indices into the intracellular recordings table. Now, if we don't know these row indices, then we can simply query our intracellular recordings table. For example, if we only know the IDs rather than the row index, then we can simply call NW file intracellular recordings to get the table, get the ID column, and then compare against the list to then get the corresponding indices. So we then next populate our sequential recordings table. All these processes now go very similar. Our sequential recordings table has a set of reference to the simultaneous recordings table. It has a stimulus type and again an optional ID that we can define. We then populate our repetitions table with reference to the sequential recordings table, and then finally the experimental conditions table, which references our repetitions. And then in order to write the data to file, nothing changes. We call our NWB HDF5 IO as usual and write the data to file. The ICEphys extension provides also a number of enhancements to ease visualization and interaction with the data by allowing us to convert these tables to pandas. We can convert individual data tables to pandas via the .toDataFrame function, which I already showed you for the intracellular recordings table on an earlier slide. But it also supports the creation of the normalized hierarchical data frames via the toHierarchical data frame function. What this means is that the function collects all the data from all the tables that are being referenced by the current table. So in this case, we have the simultaneous recordings table, which references the intracellular recordings table. And so when we call toHierarchical data frame on that function, you can see that it creates for us a hierarchical index, which consists of the ID of the simultaneous recording. So you can see there are 4 simultaneous recordings, and the simultaneous recording with the ID 10 consists of 3 different intracellular recordings with the associated metadata, so that we now have all the data from these different tables denormalized in a single table so that we can easily query and interact with it, while at the same time we avoided data replication in the file by having it defined in the hierarchy, which also has the advantage that we can populate the data sequentially as the data is being acquired, so that this approach is also much more amenable to how data is being acquired rather than if we were to store everything as a single large denormalized table, which would require us to populate all the information at once. We can also use the toDenormalized data frame function, which is similar to the toHierarchical data frame. The primary difference is that instead of having a multi-index on the rows, which hierarchically groups the rows, this completely denormalizes a table. It's a flat table where all the data is being replicated in the columns. So here we have an example for the experimental conditions table, where you then see, for example, that the experimental condition with ID 40 is being replicated 5 times, and then all the metadata associated with this also replicated. The advantage of this approach is that, again, it provides us with a nice table that is easy to query and interact with and visualize and use. So in summary, the NeuroData ICEphys metadata extension introduces a number of broadly applicable new features. In particular, it adds support for tables with subcategories via the new aligned dynamic table type. We saw this being used for the intracellular recordings table. It adds support for the hierarchical organization of tables, which the base components exist already in NWB, but the features of how we use these is new to the extensions. It allows tables to be populated iteratively the way they're defined. So this again allows us recordings to be added iteratively as they're being acquired. So this approach is amenable to how data is being generated in a lab. All tables are optional and can be created and populated iteratively as they become necessary. So that, for example, if we only have a single set of simultaneous recordings, then we may only have an intracellular recordings table and a simultaneous recordings table, and we may not need the other tables. But as we acquire more data, we can then populate these different tables. This approach explicitly defines and describes the hierarchy of ICEphys experiments and their relationships. It avoids replication of metadata by allowing us to add the metadata at the appropriate levels in the hierarchy. Relationships between the different levels in the hierarchy are described explicitly via references between the table. The relationships between stimuli, response, and electrode pairs are modeled explicitly in the intracellular recordings table so that we no longer need to do complex queries across sweep number, for example. And we try to use explicit names as much as possible to make sure that the intent of these different tables is clear, not just by the description, but by the name. This approach is compatible with NWB 2.0. No changes to patch clamp series or intracellular electrode, for example, are required, but it really only adds additional optional structures that enhance the organization of the metadata. It facilitates metadata queries, and we're also working on support for visualization of this data with NWB widgets. And by using NWB extensions to develop this, it has allowed us to explore and evaluate this new feature before making it available to the NWB community as part of the data standards. And it has been extremely valuable for us to use the extension mechanism in that way because it allowed us to iteratively refine the definition of this extension and really identify where potential problems are along in the development process. And with this, I would like you to thank you for your attention.